You are given an array routes representing bus routes, where routes indexed at I is the bus route that the ith bus repeats forever. Every route contains one or more stations. Okay. And that's every entry inside routes contains one or more stations. And you have also been given a source station, SRC, and a destination station, DEST. Return the minimum number of buses someone must take to travel from source to destination, or return -1 if there is no route. So it's like Google Maps Lite, essentially. It's no surprise that Google asked this question, and Uber. And so in this example, this is our routes array. So this is the ith bus, the 0th bus. These are the stops for the 0th bus. And these are station IDs. And these are the stops for the 1th bus, right? Because it's at index 1, this is at index 0, and these are her stops. Now it does it perpetually, so it's a cyclic graph and it's directed. It's from 2 to 5 to 7, back to 2, as you can see here. So this is bus 1, the red bus, as you can see, denoted by red. And this is the blue bus, denoted by blue lines, blue edges. So from 4 to 6 to 7 ad infinitum, to infinity and beyond. And then, so what is the minimum number of buses we need? Buses, not stops. So we need one bus to go from 2 to 5 to 7, and then another bus to go from 7 to 4 to 6, because our source is 2 and our destination is 6. Now this gets more confusing. You can see why using code would be nice, to be frank. But we have like 6 stops, but only 3 buses. So we return three buses. And you notice we didn't use the yellow bus in this case to move from 1 to 9. Okay, so as you can see, very hard to do visually, like just to visually inspect and come up with it. But with code, it's light work, relatively speaking. And so let's jump into the solution. And it's a lot of stuff. But let's take it one at a time. The solution starts by creating an adjacency list that maps each station to the buses that travel through that station. So we're going to create an adjacency list. The key is going to be the station ID, and the value is going to be each bus that goes through that station. Okay, so let's look at that. So we have this function, right? We get our routes, or an array of arrays, source and destination. Then we're going to create an adjacency list. What does it do? The key is going to be the station. So, and the value is going to be the buses that go through that station. And so we're having a loop inside a loop, which these are the things that contribute to the complexity of the problem and make it hard. So we're looping through all the routes, right? Now we know that in each for each route we have a list of stations. So for that particular bus, so these are all the stations for the ith bus, and then we're going to loop through each of those stations, right? So that we can get each individual station, use it as a key in our list, as you can see here, and either initialize it. Not either, actually. Initialize it if it hasn't been initialized yet, and then update the bus, that particular bus, because remember the cursor here is the bus ID essentially. So that's how we construct that matrix. And I'll go over this again when I use the diagram, but let's go through the text. And so they're explaining, we iterated through the routes, and for each route add its index to the list for each station in the route. We just did that. Next, we use a breadth first search algorithm. So anything BFS, you think you're going to use a queue of some sort to find a path from source to destination. So this is like very akin to like the topological sort type of thing. So we want to find a path from the source, and there's a whole series on that a couple of videos back, a playlist even. We want to use BFS to find a path from source to destination using a minimum number of buses, since BFS always finds the shortest path in an unweighted graph. The BFS algorithm is implemented with a queue that stores the current station and the number of buses taken to reach that station. Okay, the queue is initialized with source and buses are kind of 0. I'm torn between two things. Let's keep reading. Okay, so yeah, we have our queue for BFS. We initialize it, or where is it? We initialize it with source and a bus count of 0. So because to get to the source node, it doesn't cost you anything, right? There's no bus. The first bus is you're already at the source node, so it didn't take you any bus to get there. So that's why we initialize it like so. And then we repeatedly dequeue the next station from the queue. And if it's equal to the destination, we return the number of buses so far. So we're going to be incrementing our bus count and updating where we are currently. Okay, so the queue stores in a tuple where you are currently, how many buses it took you to get there. Okay, pay attention to that. And we repeatedly dequeue, and this pattern shows itself time and time again whenever you're doing BFS. You're checking while the queue is empty, while the queue is not empty, then you dequeue, you remove something from there, and you're always going to end up adding something. So anytime you remove something from the queue in BFS, know that you're going to probably add something if necessary. As you can see, we do down here. And so when you dequeue, we take, the station we're at right now, how many buses we've taken so far. If we see that we're already home, right, just return the number of buses taken. Boom, we're done. Otherwise, if we're not there yet, we're going to do stuff that makes this problem a hard problem. Lots of nesting, lots of conditional checking, right? And this comment might be instructive. If the station is in the graph, then iterate over the stations in the graph, and if it is not already visited, enqueue all the stations in that bus route along with the incremented bus count and mark the bus as visited. That's confusing to me. And so ignore that in its entirety. But so I think you're saying the same thing here. We're going to iterate through the buses that travel through the current station. So we know what station we're at. And so we want to loop through all the buses that go through that station. Remember, we've constructed that prior. And so that's what's happening here. We look up the station in the adjacency list, and then we're going to loop through all the buses that pass through that particular station that we're in. Remember, we just queued it. So we're looping through all the buses that pass through the station that we currently at. And if we've not used the bus before, and then we have this visited buses, that keeps track of whether we've used this bus before. Okay. For each unvisited bus, we enqueue all the stations that a bus in that bus route. So all the stations that bus takes, along with the bus count incremented by 1, and mark that bus as visited by adding it to the set of visited buses. Okay. If the queue becomes empty and no station is equal to destination, return -1, because there is no route available from source to destination. I think in this case, this is one of those problems where this is the beginning of the video. The solution, anyway. The diagram is king, pretty much. So imagine we had these routes and these two buses denoted by the red and what is this, teal, bluish green, kind of blue, but like a hint of green in there. And so we construct a graph. This is what it looks like visually, but in our adjacency list, this is what it looks like. And the key is the station. Right? The key is the station, and the value is an array of the buses, the bus IDs, bus 0, bus 1, right, that go through that particular station. And so the first thing we do is on queue, right? We start off at 2 because they told us our source is 2 and our destination is 6. So we start off at 2, and it didn't take us any bus to get there because that's our starting point. So we seed our queue with 2, and that's what happens in here, right? We've created the list that corresponds to this over here. Right, this is the list right here that we created over here. Next, we seed our queue, the source bus stop, and the number of buses it took us to get there, which is 0, as you can see here. And then we have this visited buses set that we just initialized, and we're gonna loop until the queue is empty. So take the first thing out of there, and they do that right here. So take the first thing, deck or dequeue an element from the queue and store its values in station and bus taken. And that's what's being destructured here in JavaScript parlance. So we have the station, we have the buses, number of buses you've taken. Then, okay, we are here currently, right? And it took us this amount of buses to get there. If we are already there, then just say, oh, we're here. Return the number of buses it took. Okay, but if that's not the case, okay, so, and that's what happened here. So we're going to get the bus number, okay, from station 2. So we're at station 2, and we're going to get the bus, retrieve what's in here from the adjacency list and add it to visited buses, and that happens here. Okay, so we looked up everything in the adjacency list. Then we go through all the buses that pass through that particular station, and in this case, station 2, the only bus that passes through station 2 is 0. And so we added, okay, we've used this bus. Okay, so update the set and add all the stops for that bus that passes the station. So in this case, 0. 0 is what passes through the station. And so we are going to add every single stop for bus 0 into our queue and update those other stops with the +1. Okay, so 2, station 2, we're gonna add 1 from here, right? Basically 2, 1, 5, 1, 7, 1, as you can see there. Okay, that's the first step, first cycle. And then so we dequeue 2, now we added 2 again, right, that we just saw, which is our source, but this time we updated the bus state into 1 for every single entry in here. And so we know that we've seen this before. Okay, so we've seen this before, and there are no other buses passing through to that station. So station 2 has no other buses. So, and we've seen this bus before, and so therefore we move to the next iteration. So this branch basically doesn't trigger, right? That on queue is the same thing over and over again. This doesn't trigger. That's what they're trying to say. And so we move to the next one, the next station. And that's because we dequeued, right? The next station was the next thing there, right? So we dequeued it from there. So we're looking at 5 this time. And because we've in station 5, we then want to get all the buses that pass through station 5. However, there's only one bus that passes through station 5, and we've seen that bus before, so this branch doesn't execute. Okay, it doesn't ever execute. And so we move on to the next station, which is 7. Now this has one bus that we've not seen before. It has 0, so for 0 none of this would execute, but for 1 it is going to execute. So it's going to go through bus 1 and add all its stops to the queue. Okay, as you can see, and also increment the number of buses it took, because now to get to these places you should have taken bus 0, which counts as 1, and then to get to 4, either 4, 6, or 7, you should have taken another bus, which counts as 2. And so you keep moving. You dequeue again, the cycle goes again. We're at bus 4. We've seen 4. Remember, because of this one here, we populated the queue again. So when we come to 4, we've seen 1 before, so that special branch again doesn't happen. We're not on queuing anything or updating the visited, because we've seen that before. And till we get to 6, and then when we take 6 out of there, 6 is our destination, right? So this check happens and then it breaks. Okay, we're now return the number of buses and we're done. And if we do every single thing and nothing works, we just return -1 out here. Okay, and that's all there is to this problem. It's quite a doozy, lots of nested loops and if statements. Not my best. Well, I mean, not my best solution, but I hope it's useful to you. If it is, like, comment, subscribe, share, and who knows, maybe I'll do this video again sometime down the line, but I think it should be clear enough. It's already 15 minutes long. And so the time complexity is R by S, where R is the total number of routes, S is the number of stations. Space complexity is the same. So R by S, R is the total number of routes, S is the total number of stations. Okay, that's all there is to it. Thank you so much for watching. See you in the next one. Bye-bye.